So here we have some ACS Gen Chem 2 practice problems working with dynamics. So let's get into it. Which reaction coordinate diagram represents a reaction in which the activation energy is 50 kilojoules per mole to the -1 and delta H reaction is -15 kilojoules per mole to the -1? So this is really easy. I'm going to draw a reaction coordinate graph so you can, and I'm going to map out, I don't even have to draw this, but I will. So this part is the delta H of reaction. And this bump right here is going to be the activation energy. So we're going to see these on all the graphs, and if the delta H of reaction is negative, like what's noted here, we need to look at the ones that are negative. So right here, this one's negative because it's going down from the reactants. And this one is also negative. So these two, the delta H of reactions, are positive, so we can already get rid of those because we don't want that. Activation energy is 50. So if we look at this one, we see this is around 40, it looks like. It goes to 90, so this activation energy would be 50. So that's correct, but let's look at this one, right? So right here, we're about 60 to 85. This is definitely not it, so B is our answer. Pretty easy. Let's see. For question 5, we have the rate law for the reaction is K concentration of H2O2 to the concentration of I to the, yeah, okay. So the reaction, the overall order of the reaction is, well, these both have no exponents, so it's just 1. So combined, it's just 2. It's to the exponent of 1, it's just 2. You just combine whatever number is right here when you're given the rate law. Super simple. Okay, 6. The activity of a radioisotope is 3,000 counts per minute at one time and 2,736 counts per minute and 48 hours later. What is the half-life of the radioisotope? So they're giving us a hint there that we need, and it's radioisotope. So radioactivity is going to be our first order, so our first order reactions. So that tells us the equation that we want to use. So it says, what is the half-life? To find half-life, we need the K value, which we do not have. Let's write out what we do have. So initially, I write concentration because that's just kind of how I keep track, even though we're not talking about concentration. Just initially, we have 3,000 counts per minute. And at time, we have, so this is the one where we're given a time and a value for, so that's going to be, you know, the number we have at a certain point in time, and that's 2,736. The time we are given is 48 hours, and K, we do not have K. So how are we going to find K? Well, to write out the equation for a first order reaction, it is time equals the ln of concentration of time minus the natural log of concentration initially over the negative value of K. Time, we have 48 hours. Okay, so we're trying to find K though. Oh, so we switch these. Boop. So our natural log of the time value is 2,736 minus the ln value of 3,000 over -48. This will equal our K value, which we can then use in our half-life equation. T sub 1/2 is what stands for half-life, And this is our first order equation for half-life. And we need to find K, and that's what we're gonna solve for. Yep, and ln 2, constant, it stays there, stays at the top. So, let's just plug and chug, right? Let's see. Ln of 273. I'm gonna write this all out because I've had issues where I need to write things out before calculating because you can get messy in your calculator. Divided by negative 48. So 7.9143 minus 8. Oh, that's not 8. Divided by negative 48 gives us a K value of 1.910467. And I didn't round much because we're not done, and you don't flush until you're done, right? We're still going. You don't flush till the end. So there's our K value. We can plug that in to find our half-life, the ln of 2, over our wonderful, beautiful K value. Let's see, 1.910467 times 10 to the negative 3, and we get this answer. And I was confused when I did this prop. Okay, this is confusing. Because on our ACS, the closest answer is C, which is the correct answer. We got 363, and the answer is 361 here. I don't know what I did wrong. Let me know. But it worked, right? And we're so close. I'm sure I kind of did it right. Makes sense. Okay, moving on. The half-life for the first order conversion of... Okay, so question 7. The half-life for the first order conversion of cyclobutane to ethylene is 22.7 seconds at a particular temperature. How many seconds are needed for the partial pressure of cyclobutane to decrease from 100 millimeters of mercury to 10 millimeters of mercury? Okay, so this one, it's nicer, and it tells us it's first order, which is the same order we just worked with, so that makes it easier. And we're using the same form of the equation because we are solving for time. How many seconds? We need time, because that's what we don't know, are needed for the partial pressure. So let's write out what we have. So the pressure we have initially is 100 millimeters for mercury. Such an ugly unit. And the pressure we have with time is 10. Time we do not know, and we're also not given K. So we can use our half-life equation, which is way easier than the one we just did, because we're given the, right? Yeah, because we're given the half-life right there. So that's super easy. So we use the same half-life equation, the natural log over K. But we have half-life, which is 22.7 seconds, equals ln 2 over K. So switch these guys and calculate it. So ln of 2 divided by 22.7 equals this K value. Boop, boop, boop. 3.0535 times 10 to the negative 2. Super easy. And after that, what's it asking us for? How many seconds we needed? Okay. So let's do it again. This is our K, so yeah, literally the same exact equation. So T equals this of did I not like write this one out? Where did I solve this one? So solving this just like we did the last one, time equals the ln of 10 minus the natural log of 100 over negative our K value, which we just calculated. And let's do this one. Oh, that's not negative. And so we get in seconds 75.408, and perfect right here, B is exactly that. A plot of reactant concentration as a function of time gives a straight line. What is the order of the reaction for this reactant? So I went ahead and wrote out all the graphs for every order. And we're looking for concentration versus time. Straight line, of course. And concentration versus time gives us a straight line, negative, for a zero order reaction. For a first order reaction, the natural log of concentration as a function of time gives us a negative slope. And for second order, 1 over concentration versus time gives us a positive straight line. But we are just looking for plain old concentration versus time, which is zero order, and that's our answer.